Hello everyone. So we'll see some question that is from ring theory section. So these are some question we'll see here. So okay, let me first crop the first question. Okay, so this is the first question. Okay, so the question says, uh, give an example of an infinite integral domain of characteristics 5. Okay, so so solution. So what is characteristics of a ring? First, we recall this characteristics of a ring. Say are okay under addition and multiplication. Okay, so this is a ring. Okay, so the characteristics of a ring is the smallest positive integer. Uh, so the characteristics of a ring is the smallest positive integer uh, say n such that n a equals to 0 for all a belongs to R. Okay, so this is the definition of characteristics of a ring. Okay, fine. Now we will give an example of an infinite integral domain having characteristics 5. Okay, recall Zn is a field if and only if n is prime. Fine. Okay, so take R equals to Z5. Okay, so this is a field. Okay, and we know if R is a field, then if you define uh, polynomial ring, that is Rx, then it is ed PID, and every ed PID is integral domain. So Z5x is an integral domain and which is infinite, and it is of characteristics 5. So this is the example. Okay, so now we go to the next question. So yeah, okay, okay, so the question says, let R be an integral domain and I be an ideal of R. Okay, then the question ring, that is this, sorry, then the question ring this is an integral domain or not. Okay, we know solution. We know if R is integral domain and I is prime ideal, I is prime ideal, then the quotient ring is integral domain. But if I is not prime ideal, then this is true or not? This is not true in general. For example, okay, for example, let R equal to Z and I equal to 6Z. Then R over I, that is Z over 6Z, is not integral domain. Why? Since if you take two element from R over I, that is 2 plus I, 3 plus I element of this, then okay, we should write tick. Then the product of these two element will be this in Z 6Z. Hence 2 plus I and 3 plus I are 0 divisor of this. So we get the conclusion, that is R over I is not integral domain. Okay. Okay, now we'll see the next question, that is this one. Okay, so this is an interesting question. Okay, fine. Okay, let Nm be distinct positive integers. Prove that Nz is not isomorphic to Mz as rings. Okay, so solution. Okay, we'll prove it by contradiction. Suppose there is exist a okay, right, suppose there is a ring homomorphism say phi from Nz to Mz. Okay, since Nz, which is generated by N under addition is a cyclic group. Okay, and Mz under addition is a cyclic group and which is generated by M or minus M. Okay, so since phi is a map from Nz to Mz, so phi of N either M or minus M. Okay, and phi is homomorphism. Now phi of N into M, that is phi of N plus N plus phi of N times. We can write it by using the properties of homomorphism. And we'll get here Nm or minus nm. Okay, from the above this. Okay, now also phi of n into n is phi of n, which is nothing but m into m square. Okay, and we have given in question that n and m are distinct. Since n not equal to m, so nm not equal to m square and minus nm not equal to m square. So therefore phi is not well defined. Thus these are not isomorphic as ring. So this is the proof. Okay.